Okay, our final speaker, I think we'll take the ball that Scott has thrown him and run with it. This is Michael Amaker. He works at the Rocky Mountain Research Station, just adjacent to the campus here. His main areas of interest have been restoration of disturbed lands, disturbance ecology, forest health indicators, specifically soil as an indicator, soil quality monitoring, and reactions of transport in soil and water systems. So, Mike?
Okay, thanks, Paul. Now for something new and different. About a decade ago, Dale and Bob Campbell published a paper summarizing a lot of the ecological benefits of Aspen. Many of these have already been covered so far in this conference, and we've talked about more. So I'm not going to go through them, but this is by way of introduction. But at the very end, I'm going to add one more down here. One more ecological benefit to this entire list. And this is by way of review here. Threats to the Aspen community have been pointed out: fire suppression, overbrowsing, ecological succession. I don't think I need to dwell on this. This is more set the stage and introductory material. Now to bring soils into this. Soils are a product of 5 soil forming factors. The properties of soils as they exist on the landscape are due to the interaction of all 5 of these. We've got parent material, landscape position, biota, and vegetation will be in here, climate, all acting over time. So different soil properties can develop under different vegetation regimes. And a lot of what I'm going to talk about today is going to focus on this soil forming factor here, the biota, or more specifically, vegetation community types. A number of years ago, Cryer and Murray published a model of Aspen conifer ecological succession and associated soil changes that could occur with that. And under Aspen, you tend to have more molic horizons. Under climax spruce fir, the horizons tend to be more leached albic horizons. This is a list of the soil types here. But in general, organic matter and nutrients tend to decrease going from stable to climax spruce fir. CC, base saturation pH, tends to decrease. Soil temperature tends to decrease. This is what Cryer and Murray said is likely to happen as you move from here to here. And one of the points they brought up is, once you get to this point, can Aspen even come back on the landscape? Or do you need some drastic measure like fire to realign the soil, change the soil properties, add more nutrients to drive it back this way? Or is that even possible? So this is the overall Cryer-Murray model. We were very intrigued by that. So we did some work about a decade ago on the Fish Lake National Forest and showed that the mixed aspen conifer stands down there had not progressed too far that you could preclude aspen recovery on the landscape. And indeed, numerous treatment projects down there and on other national forests and elsewhere have shown vigorous aspen regrowth following various treatments of mixed aspen conifer stands. But that still begs the question, what happens if you have dominant spruce fir long enough? Well, fortunately, we now have the means to carry out an end-member analysis, comparing soil properties in forest types dominated by spruce fir and other conifers with aspen. And that's basically what I'm going to talk about for the rest of the time. I need to tell you something about what FIA is. That's the Forest Inventory and Analysis Program. It's a continuous annualized inventory of the nation's forests across all ownership categories. It's basically the nation's forest census. Collects and reports data on the status and trend of forest area location, species size and health of trees, so on and so forth. And there are some forest health indicators data that are also now collected by FIA. And here they are. They include crown condition, ozone injury, tree growth damage and mortality, lichen communities, understory veg, downwoody material, and finally down here, soil quality. And this is the one I'm going to talk about today. Some of the attributes of the soil indicator within FIA, and this is shared with the other indicators, it's a status and trend assessment at multiple spatial and temporal scales. So it's a detection monitoring grid of soils-related forest health problems. It's integrated with other forest health indicator data. It's a standardized, unbiased, grid-based measurement and sampling design. That's an important point of this. It's national and comprehensive. All U.S. forest lands regardless of ownership. All ecoregions, all forest types, all forest soil types. It's standardized, reproducible, nationally consistent protocol, nationally consistent training. There's a QA/QC program for the labs and for the field work, and there's even some standardized estimation and reporting. It's why we call it the one true soil monitoring program. There is simply nothing else like it anywhere in the country. This is what it looks like as part of the Forest Service Integrated Monitoring Framework. Remote sensing detects the forest lands. Here's FIA here. There's two phases to it. The forest inventory, which collects the tree data, and then phase 3 collects the forest health data, including soils. And there's almost 8,000 permanent forest plots on a 13-mile grid across the country. Or there will be 8,000 by the time they're all visited. Looking at the scale of the sampling grid, here's a very coarse hexagonal scale here, but you can tessellate these across the landscape at any scale. Here's one sitting over the U.S. This is a forest lands map of the U.S. But carrying it down to the state level, this is what the phase 1 spatial grid would look like for detecting forest lands, 3 million points across the U.S. Phase 2, collecting the tree data, is about one plot for every 6,000 acres, and so that's what the grid intensity looks like for that. Phase 3, 7,800 plots across the U.S., and in the state of Minnesota, about one plot for every 96,000 acres, using Minnesota as an illustration here. This is about what the grid intensity would look like. But the same grid is used in all the states. This just gives you an illustration of what it looks like going from phase 1 to phase 3 in terms of grid intensity. Here's all the soil plots for 3 years worth of data here. We actually have quite a bit more filled in here now because we're up to 2008. We just haven't updated the map yet. Think of FIA as a belt transect 3,000 miles long and about 1,500 miles wide across the conterminous United States. This year we moved into coastal Alaska. We're in Montana already. New Mexico hasn't come online yet. Hawaii has not come online yet. I think Mississippi and Oklahoma are now online. So the actual, once we update this map, there'll be a lot more yellow points filled in here. So this gives you an idea of the scale at which we operate within FIA. The standard plot design looks like this. It's basically circular plots in a triangular shaped layout here. Data is collected in subplots. There's 4 of them. Samples are collected in the angular plots surrounding the subplots. Angular plots are reserved for destructive sampling because with soil sampling we have to take away a sample. In the soil indicator, we have an erosion assessment, a soil compaction assessment, and some soil sampling, and this is what I'm going to talk about today. We do measure forest floor litter thicknesses. We take a sample of the forest floor. We sample the soil cores, 0 to 10 and 10 to 20 centimeters. Soil texture, I'm just going to focus on data from here. These are all the things we measure in the regional FIA labs. A number of physical properties of the forest floor, a number of chemical properties, including carbon and nitrogen, some physical properties of the soil cores, chemical properties, carbon, nitrogen again, pH, exchangeable cations, extractable phosphorus, and so on. And today I'm going to show you some of this data for the West and across the country. All right, let's get into some post-data collection stratification here. What I've done is I'm going to talk about the data stratified by general forest type groups in the interior West, and I've arranged them here by increasing latitude, elevation, and decreasing temperature from the drier site type of forest on up to the subalpine forest. Now, within each group are the forest types listed here, and there's overlaps among the forest types. These are not, all mutually exclusive. There's even overlaps of the tree species within forest types. But nevertheless, to get started on the data analysis, we needed some sort of stratification. And so this is what we've begun with. How many plots of data am I going to show you? Well, 941 total collected over about a 6-year period here. Here's Aspen. We have data for 67 plots so far. In the Cottonwood Aspen Birch group, 72, so it's dominated mostly by Aspen. Spruce Fir, which is mostly what I'm going to compare against, we have data from 131 plots across these 5 states listed here, mostly Engelmann spruce, mixed spruce, and subalpine fir and subalpine fir. And PJ is the largest group of data we have. Some of them we only have data from one plot. To give you an idea of the distribution of the forest types for the data set we have. Okay, prepare yourself for an avalanche of data here. That's what I'm going to show from here on out, most of the slides. On the right-hand side is going to be regional data, data organized by region to give you a regional context. And then on the left-hand side, I've got the soil type or the forest type groups in the interior west arranged as I showed you earlier, ranging from lower to higher latitude, from lower to higher elevation, from drier to wetter, and so forth. This is forest floor water content. You can see there is a moisture gradient, as you would expect, going from drier forest types to wetter forest types. There's a huge moisture gradient across the country. Here's the interior west here. And within the interior west, by forest type group, it looks like this. For the soil cores, water content, a similar gradient. Here it is across the country. Bulk density data. Notice there's a gradient by elevation and latitude in bulk densities. Here's Aspen. Here's spruce fir. Aspen, spruce fir is the gray here. We're mostly going to be focusing on these. This gradient here is mostly due to changes in soil organic matter, as you're going to see coming up here. The single most dominant factor controlling soil bulk density in forest soils is organic carbon. This is on a log scale here of organic carbon. Here's bulk density. The 5 FIA regions here, the 0 to 10 soil cores, the 10 to 20 centimeter soil cores. You can see there's an exponential relationship. This is plotted on a log scale here, so it comes out as a more or less straight line cluster of plots here. But basically, as you have more organic matter in the soil, the lighter and fluffier it is, so the lower the bulk density. So looking at the forest floor, let's look at the carbon and nitrogen contents of that. Here's aspen, here's spruce fir. They're about the same in organic carbon concentration. But aspen forest floor samples are much higher in nitrogen than spruce fir, and indeed they're the highest in the interior west. So the carbon-nitrogen ratio of aspen is much less than that of spruce fir and most of the other forest types. There is an enormous nitrogen gradient across the country. This here in the northeast is due to large atmospheric deposition of a great deal of nitrogen. I mean, you can lay a ruler across that. And here's the interior west, kind of low overall compared to other parts of the country, but within the interior west, this is what the breakout looks like. And here's aspen up here. So if we look at the mass of forest floor, here's aspen, here's spruce fir. Aspen doesn't have, a massive forest floor sitting underneath it. So the carbon level, the mass of carbon in megagrams per hectare in aspen forest floor is actually less than spruce fir, and same for the nitrogen stock in megagrams per hectare is less than spruce fir. And here's the regional data here. There are large regional differences, but there is a bit of a gradient here. as you can see. Now, if we look at the soil cores underneath the forest floor, for aspen and spruce fir, they have about the same carbon concentration. But nitrogen soils are much enriched in nitrogen, aspen soils, compared to spruce fir, so their carbon-nitrogen ratio overall is much less. So this, you saw that earlier slide showing you the bulk density gradient. Well, here's the reason why this carbon gradient here in the soil cores underneath the forest floor. So even though spruce fir and aspen have about the same carbon content, their nitrogen contents are greatly different, so the carbon-nitrogen ratios are greatly different. And when we summarize that all together, here's the total carbon stocks by forest type, the total nitrogen stocks by forest type, and the regional data here, large carbon gradient across the country, significant regional differences in total nitrogen. Aspen actually has the most carbon in the soil under the forest floor, but because its forest floor mass tends to be less than that of the higher elevation conifers, you end up with this kind of a comparison here. But in terms of nitrogen, aspen is the champ in terms of nitrogen storage, because there's so much more in the soil under the forest floor than there is in spruce fir or the other higher elevation conifers, by a hugely significant amount. Just compare that bar height with this one. Okay, a little bit of explanation of all this now. Factors that control soil organic matter accumulation and decomposition, or organic matter composition, basically fresh plant residues and things like that will break down very quickly, stabilize soil organic matter. This is the stuff that persists in the soil. You have temperature and moisture controls carbon and organic matter accumulation. You'll get a lot of breakdown in carbon the higher you go in temperature, except under wet moisture regimes here, which is why carbon can accumulate in coastal marsh soils in Louisiana and places like that, even though the temperature is very high, because the soils are saturated, they're wet, they're anaerobic, so you don't get the carbon oxidation. So there's an enormous environment effect, enormous composition effect, and you can predict decomposition pretty good just using a simple measurement, carbon-nitrogen ratio. This is a very common list here. I got this from the Washington State University. Here are things with high carbon-nitrogen ratios that break down very slowly, things with narrow carbon-nitrogen ratios that break down very quickly. Aspen tends to lie right in here. The conifers would be down here. So this stuff decomposes very rapidly. This stuff down here decomposes very slowly. So putting all that together then, we would expect to find more carbon accumulating in forest soils the further north in latitude you go, the higher up in elevation, and the wetter the soils. That's pretty much what our inventory map shows. You'll notice all the carbon accumulating in Maine here, upper Michigan Peninsula, and so on. This is the forest floor data. This is the soil cores underneath it. And that's very much what we would expect, and that's what we see. So to summarize the situation for aspen compared to spruce fir, for example, you've got a high organic matter input from understory veg. You tend to have warmer soil temperatures, although I haven't shown you any soil temperature data. We did put out a paper comparing the two, and they are different. So you've got a high litter decomposition rate under aspen here from these leaves in this understory veg because of high nitrogen and lower carbon-nitrogen ratio. So it maintains its high organic matter level with a high turnover of organic carbon. Spruce fir, on the other hand, you tend to have a low input from understory veg, cooler soil temps, slow litter decomposition rate because of low nitrogen, higher carbon-nitrogen ratio. It simply maintains its higher organic matter level due to a low decomp rate. So if we go back here, see the carbon levels of these forest types are about the same, the nitrogen levels are very different. So this one, they both have the same amount of organic matter, but this one is doing it via high turnover. This one is doing it because things just aren't decomposing all that fast. There are some other crucial differences in soil properties. Sodium is about the same, but aspen soils store about double the amount of potassium as spruce fir. The West has a lot of exchangeable potassium in its soils compared to forest soils in other regions of the country. Magnesium too. Magnesium is fairly high in aspen soils, much higher than spruce fir. It even rivals forest types in the more arid regions where the calcareous soils dominate. For the higher elevation forest types, that's an awful lot of magnesium and a heck of a lot of potassium. Soil pH. Aspen soils tend to be slightly acidic. Spruce fir soils, a whole pH lower. Enormous pH gradient across the country, as you would expect because of soil weathering and the dominance of calcareous soils in the west compared to the east. And the consequence of that is, at low pHs, you have a lot of high exchangeable aluminum in the soil. Calcium tends to be lower. There's a threshold at about pH 5.5, whereas exchangeable aluminum will shoot way up as you go down in pH this way. And a consequence of that, when we start comparing the forest types with each other, aspen has a lot more calcium than spruce fir, a lot less aluminum. Aspen simply cannot survive at these aluminum levels. And so the calcium-aluminum ratio under aspen, much higher than under spruce fir. And here are the regional differences again. The Northeast has high aluminum. Calcium depletion is very severe in the Northeast. The West is way down here. Hobie and I have recently done some work putting together the distribution of calcium-aluminum molar ratios by forest types across the country. So now we're going to throw in eastern and western aspen. And you just don't find aspen when the calcium-aluminum ratio drops below about 1. Spruce fir, on the other hand, it can live quite nicely at higher calcium-aluminum ratios, but it does survive where aspen can't, down here. We've summarized all of our soil properties in a derived index we call the Soil Quality Index. And we published a paper on that recently. Aspen has the highest soil quality index of all the forest types in the interior West, by far. The lower the soil quality index, the higher the risk of soil-related forest health decline. So putting all that together, I'm adding one more ecological benefit of aspen to Dale's and Bob's list here, and that's storage of nutrients on the landscape, especially nitrogen, potassium, and calcium. So that then brings up the original question, why we looked at all this data. What is the ecological consequence then of aspen loss and long-term replacement by conifers, particularly spruce fir? Well, you can have loss of nutrient storage, increased soil acidity and toxic levels of aluminum here. So if spruce fir occupies former aspen soils long enough as a result of ecological succession, aspen is not going to return because it's not going to tolerate calcium depletion, high aluminum, low pH. A lot of potassium is going to be gone, and a lot of nitrogen is going to be gone. So potentially you could have irreversible soil changes if you had spruce fir dominating previous aspen soils for a long enough period of time. It would be very difficult to go back the other way. Spruce fir will invade into aspen, but aspen is not going to invade back into spruce fir when it has these kinds of soil properties. And that's basically the take-home message from all of that. Yeah, that's it.
Questions?
Yes.
What sort of time interval would you guess it would take to have a spruce or a conifer overtake the Aspen stand before the Aspen stand couldn't come back?
That's the great unknown right now. I think they would have to occupy the site for some decades, maybe a couple centuries or more. We don't really know yet. What I've shown you is the end member analysis. A refinement of this would be a gradient type of analysis, where you looked at proportions of aspen and conifer relative to each other, and then looked at the changes in soil properties along that ecological gradient. But that is a question we potentially can answer through time, because the FIA data set was set up to do not just status, but status and trend. The soil sampling is done every 10 years. So in time, we actually will have an answer to that question. Right now, I just can't tell you, well, 90 years and that's it. There's no way I can come up with a number that precise.
Do you have a sense of what the threshold for that calcium aluminum concentration is before it would cross over that line?
Yes, based on the analysis Hobie and I have done so far, if you've got a calcium aluminum ratio that's dropping below 1, Aspen would be almost impossible to occupy that site again. And in lieu of any other evidence, we'll go with that ratio for now.
Yeah. It's really interesting to see the contrast between aspen and the other forest types in terms of soil. I wonder if you would have an opportunity to sort of drill in on the aspen types and look at the variability within those and tie soil differences to canopy condition, breakup of the aspen stands, the types of problems in the shading aspen, and see if those are more prevalent associated with some soil properties than others.
Potentially that could be done, more of a gradient type analysis. We already have data from 67 active forest types in which aspen is dominant. Now the tree data does exist for those plots. So someone could go back in and say, okay, we're going to refine this analysis a little bit more and start looking at the proportion among the different individual trees within the forest type and so on and so forth to get at some of the analysis that you just mentioned. That could be done. It would be better done if we had data from more states in there, because we need large databases for that type of analysis to reduce the error.
Yeah. Mike, it's an implication question. Would the response to burning versus mechanical harvest be the same or different on the effect of the carbon or the calcium ratio?
So it'll be different, and that was one of the things that Cryer and Murray brought up, that if you have spruce fir on the site for too long, you better burn it rather than cut it, because wood ashes will line the soil to some extent. The ash bed effect will add some nutrients, including calcium, back in there, and you might be able to drive it back the other way. But if aspen roots have been eradicated from the site because spruce firs occupied it for decades, I'm worried about where the aspen root's going to come from if there's no longer any aspen component in that forest. Now granted, this was an end member analysis, so, looking at what is the worst case scenario that could happen. If you wait too long, that's what could happen. But I can't tell you, well, if you have one lone aspen left, you can recover the site, because I don't know that.